For our class project, we were assigned alkali metals.
Alkali metals are highly conductive of heat and electricity. They also have a metallic luster and are quite malleable. As you can see in figure 1, this sodium metal was freshly cut, so the cut part is quite metallic, but the outer surface has already been oxidized by the atmosphere and now has lost that metallic luster. It also has, as a group, electronegativity and has the lowest ionization energies of the periodic table. It also has pretty low melting points, and these melting points decrease going down the table.
The electron configurations for the alkali metals are as follows. Lithium is 1s2, 2s1. Sodium is 1s2, 2s2, 2p6, 3s1. Potassium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Rubidium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. Cesium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s1. Francium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s1. Important chemical reactions involving the alkali metals. They are good reducing agents, and then I'm sure everyone's seen the demonstration where sodium gets thrown into water and it explodes. They all react pretty violently with water, and these explosions release more heat as you go down the group. And then they are so sensitive and reactive that they will react with oxygen in the air to form oxides, which is why usually when you see alkali metals, they're stored in some sort of oil to prevent this from happening. And then potassium, rubidium, and cesium specifically form something called superoxides. Some more important reactions is when they react with ammonia, they give solvated electrons in solution. These solvated electron solutions are great reducing agents, better electrical conductors than the salts dissolved in water. They're also paramagnetic, and they are larger in volume than you might expect, and it's because these electrons create these pockets around themselves. And then the solutions, the solvated electron solutions, will eventually decompose, resulting in an amide.
So some really important useful chemical reactions of alkali metals is in the Birch reduction, which is a useful reaction for de-aromatizing compounds in a specific way. It was initially discovered by an Australian chemist named Arthur Birch in 1944, and depending on whether you have an electron donating group or electron withdrawing group, you'll get specific reduction about the different double bonds. Another really useful and important chemical reaction of alkali metals is when they come in contact with benzophenone in special solvent stills that are known as ketyl stills. So the metal can react with the benzophenone to make something that's called a ketyl anion. And this ketyl anion has a very deep blue color, and it's used to destroy the water that it's found in solvents like THF, diethyl ether, hexanes, DME, and 1,4-dioxane. This solvent, this is a very useful thing for synthetic organic labs because it's an easy way to make anhydrous solvents for use in reactions.
Alkali metals can also be used to generate alkoxides. Alkoxides are the conjugate bases of alcohols, and they are also very strong bases. Tert-butyl alkoxide, also known as tert-butoxide, is a commonly used non-nucleophilic strong base. Alkoxides are also used in the Williamson ether synthesis.
I guess the final really important chemical reaction that we went over was crown ethers. So just a big organic compound with 6 oxygens in it, and the oxygens donate their electron density. And then crypans are just better crown ethers because instead of 6, they have 8 oxygens.
So alkali metals are quite reactive, so they have quite a lot of relations to other groups. The most obvious one is the relations with halogens, as they have a +1 charge and halogens have a -1 charge. So they react in a stoichiometric ratio of 2 to 1 because halogens are diatomic. And so they have a stoichiometric ratio of 2 to 1. And alkali metals can also react with heavier group 16 elements such as sulfur, selenium, so ones lower down on the periodic table, and they react in a 2 to 1 stoichiometric ratio. Only lithium reacts with nitrogen in the atmosphere to create lithium azide, and it also reacts, alkali metals in general react with the heavier group 15 elements such as arsenic and phosphorus in a 12 to 1 ratio. They also react with group 14 elements, but the properties and stoichiometry of these reactions differ. And so some real life applications are that anhydrous sodium and lithium salts are often used as drying agents to remove water. They are also used in organometallics. So it is the alkali metal, which is covalently bonded to the carbon. And then methyl lithium is the most stable out of these. And some cooler applications that we might not be able to see in the chemistry department are that sodium remains a liquid from 98 to 883 degrees Celsius. So it's used as a specialty coolant in nuclear reactors as the temperature of these reactors is quite high. And cesium is used as a standard of measurement for a second, as it roughly 9 million periods of the radiation from the ground state of the cesium atom are used to define a second. And so an interesting fact is that lithium ion batteries may soon be replaced by sodium metal batteries because lithium is quite toxic to mine. So it is quite imperative that we find a new battery, new material for batteries. And so Wan and et al. Developed a solid electrolyte interface that sustainably increased the capacity retention of the battery after 10,000 cycles. And this was the solid electrolyte interface, which is on the slide. But basically, with more research, we may soon have sodium metal batteries in our computers. And these are our references, and thank you for listening.